when an electrical panel is directly connected to the service entrance point, such as the meter main, it's considered the main panel even if it's located inside the building. According to the National Electrical Code, or NEC, all neutral conductors and equipment grounding conductors, or ground wires, must be bonded together at the service entrance. This means that the neutral bus and ground bus are bonded at the meter main. Therefore, the main panel should have a neutral ground bond to ensure that neutral and ground conductors are at the same electrical potential, preventing electrical shocks and other hazards. The grounding electrode conductor, or GEC, from the ground rods to the water pipe to the meter main is crucial for creating a solid grounding system. This system establishes a low resistance path to earth for fault currents. The equipment grounding conductor, or EG, that is bundled in the Romex cable should be connected to the bonded ground bus in the meter main and to the ground bus in the panel, which is not bonded. In summary, the main panel should have a neutral ground bond as required by the NEC, and the grounding system should be properly installed. The location of the panel, whether inside or outside, is not the determining factor, but rather its direct connection to the service entrance. Here's a more detailed breakdown of the grounding and bonding requirements. Firstly, the main panel is the first panel that receives power from the service entrance, which is usually the meter. It serves as the primary distribution point for electricity throughout the building. Secondly, the neutral ground bond is a critical safety feature that connects the neutral conductor to the grounding system at the service entrance. This bond ensures that the neutral conductor and the ground conductor are at the same electrical potential, minimizing the risk of electric shock. Thirdly, the grounding electrode system consists of one or more grounding electrodes, such as ground rods, water pipes, or concrete encased electrodes that are connected to the grounding electrode conductor. This system provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the circuit. Fourthly, the equipment grounding conductor is a wire that connects the metal parts of electrical equipment, such as appliances and lighting fixtures, to the grounding system. This conductor provides a low impedance path for fault current to flow back to the source, protecting people from electric shock if a fault occurs. Fifthly, the NEC requires that the neutral conductor be isolated from the grounding system in subpanels. This means that the neutral bus in a subpanel should not be bonded to the panel enclosure or to the equipment grounding conductor. Sixthly, the equipment grounding conductor in a subpanel should be connected to a separate ground bus that is isolated from the neutral bus. This ensures that fault current will flow back to the source through the equipment grounding conductor rather than through the neutral conductor. Seventhly, the size of the grounding electrode conductor and the equipment grounding conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of these conductors based on the size of the service entrance conductors. Eighthly, the grounding electrode conductor should be connected to the grounding electrode system using approved methods, such as exothermic welding or listed connectors. Ninthly, the equipment grounding conductor should be connected to the metal parts of electrical equipment using approved methods such as grounding screws or listed connectors. Tenthly, all grounding and bonding connections should be made tightly and securely to ensure a low impedance path for fault current to flow back to the source. Understanding the difference between a main panel and a subpanel is crucial for proper grounding and bonding. A main panel is the first point of disconnect from the utility and is where the neutral and ground are bonded. Subpanels are downstream from the main panel and should not have the neutral and ground bonded. Here's how to differentiate between a main panel and a subpanel. Firstly, location. A main panel is typically located at the service entrance, where the power enters the building. A subpanel is located downstream from the main panel, often in a remote area of the building. Secondly, bonding. The main panel has a neutral to ground bond, which means that the neutral conductor is connected to the ground conductor. A subpanel does not have a neutral to ground bond. The neutral and ground conductors are kept separate. Thirdly, function. A main panel serves as the main distribution point for electricity in the building. A subpanel is used to distribute electricity to a specific area or load within the building. Fourthly, feeder conductors. The conductors that feed a main panel are called service entrance conductors. The conductors that feed a subpanel are called feeder conductors. Fifthly, of current protection, the main panel typically has a main breaker that protects the entire electrical system. A subpanel has a breaker that protects the circuits within the subpanel. Here are some common grounding mistakes to avoid. Firstly, bonding neutral and ground in a subpanel. Bonding the neutral and ground in a subpanel is a dangerous mistake that can create a parallel path for neutral current. This can cause the metal parts of equipment to become energized, creating a shock hazard. Secondly, using the wrong size grounding conductors. Using grounding conductors that are too small can reduce the effectiveness of the grounding system and increase the risk of electric shock. The size of the grounding conductor should be based on the size of the service entrance conductors or feeder conductors. Thirdly, improper grounding electrode connections. Making poor connections to the grounding electrode system can increase the impedance of the grounding path and reduce its effectiveness. Grounding electrode connections should be made using approved methods such as exothermic welding or listed connectors. Fourthly, neglecting to ground metal enclosures. Failing to ground metal enclosures such as junction boxes and panel enclosures can create a shock hazard if a fault occurs. Metal enclosures should be grounded using a grounding screw or a listed connector. Fifthly, mixing aluminum and copper grounding conductors. Mixing aluminum and copper grounding conductors can lead to corrosion and failure of the grounding system. Aluminum and copper conductors should be connected using listed connectors that are designed for use with both materials. To ensure a safe and effective grounding system, it's important to follow all applicable codes and standards such as the NEC. The NEC provides detailed requirements for grounding and bonding electrical systems, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for making grounding connections. It's also important to have a qualified electrician install and inspect the grounding system. A qualified electrician has the knowledge and experience to ensure that the grounding system is installed correctly and that it meets all applicable codes and standards. Grounding and bonding are essential for electrical safety. They protect people from electric shock, reduce the risk of fire, and ensure the proper operation of electrical equipment. By following the NEC requirements and best practices, you can create a safe and reliable electrical system. Here is an overview of NEC articles related to grounding. Firstly, Article 250 covers the general requirements for grounding and bonding electrical systems. This article provides detailed information on the purpose of grounding and bonding, the types of grounding systems, and the requirements for grounding electrodes, grounding conductors, and bonding jumpers. Secondly, Article 250.24 specifically addresses grounding of service equipment. This section outlines the requirements for grounding the neutral conductor at the service entrance, including the size of the grounding electrode conductor and the methods for making grounding connections. Thirdly, Article 250.30 covers grounding requirements for separately derived systems. A separately derived system is an electrical system that is powered by a generator, transformer, or other source that is not directly connected to the utility grid. This section outlines the requirements for grounding the neutral conductor and the equipment grounding conductors in a separately derived system. Fourthly, Article 250.50 addresses grounding electrode systems. This section outlines the requirements for grounding electrodes, including the types of electrodes that are permitted, the minimum size of the electrodes, and the methods for installing the electrodes. Fifthly, Article 250.66 covers the size of the grounding electrode conductor. This section provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Sixthly, Article 250.104 addresses bonding of metal water piping systems. This section outlines the requirements for bonding metal water piping systems to the grounding system to prevent electric shock hazards. Seventhly, Article 250.118 specifies types of equipment grounding conductors. This section details acceptable types of equipment grounding conductors, including wires, cables, and metal raceways. Eighthly, Article 300.3 covers conductors of different systems. This section outlines the rules for installing conductors of different systems such as power, lighting, and communication systems in the same raceway or enclosure. Ninthly, Article 310.16 provides ampacity tables for conductors. These tables specify the maximum current that a conductor can carry safely based on its size, insulation type, and installation conditions. 10thly, Article 408.41 addresses grounding of panel boards. This section outlines the requirements for grounding panel boards, including the connection of the equipment grounding conductors to the panel board enclosure. Understanding these NEC articles is essential for designing and installing safe and effective grounding systems. It is important to consult the latest edition of the NEC for the most up-to-date requirements. Let's consider some practical examples to illustrate the principles of grounding. Firstly, a residential service entrance. A typical residential service entrance consists of a meter, a main panel, and a grounding electrode system. The neutral conductor is grounded to the main panel by connecting it to the grounding electrode conductor, which is connected to the grounding electrode system. The equipment grounding conductors from the branch circuits are connected to the ground bus in the main panel, which is bonded to the panel enclosure. Secondly, a commercial building service entrance. A commercial building service entrance may consist of multiple meters, multiple main panels, and a more extensive grounding electrode system. The neutral conductors are grounded at each main panel by connecting them to the grounding electrode conductor, which is connected to the grounding electrode system. The equipment grounding conductors from the branch circuits are connected to the ground bus in each main panel, which is bonded to the panel enclosure. Thirdly, a subpanel installation. In a subpanel installation, the neutral conductor is isolated from the grounding system. The equipment grounding conductors from the branch circuits are connected to a separate ground bus in the subpanel, which is not bonded to the panel enclosure. The subpanel is fed by a 4-wire feeder, which includes 2 hot conductors, a neutral conductor, and an equipment grounding conductor. Fourthly, a generator installation. In a generator installation, the neutral conductor is typically grounded at the generator. The equipment grounding conductors from the generator are connected to the ground bus in the transfer switch, which is bonded to the transfer switch enclosure. The transfer switch is used to switch between the utility power and the generator power. Fifthly, a transformer installation. In a transformer installation, the neutral conductor is typically grounded at the secondary of the transformer. The equipment grounding conductors from the transformer are connected to the ground bus and the panel board, which is bonded to the panel board enclosure. The transformer is used to step down the voltage from a higher voltage to a lower voltage. These examples illustrate the importance of following the NEC requirements for grounding and bonding electrical systems. By properly grounding and bonding electrical systems, you can protect people from electric shock, reduce the risk of fire, and ensure the proper operation of electrical equipment. Let's delve into the specific types of grounding electrodes and their installation requirements. Firstly, ground rods. Ground rods are typically made of copper-clad steel or stainless steel and are driven into the ground. The NEC requires that ground rods be at least 8 feet long and 1/2 inch in diameter. They should be driven into the ground vertically or at an angle not more than 45 degrees from vertical, and should be spaced at least 6 feet apart. Secondly, water pipes. Metal water pipes that are in direct contact with the earth for at least 10 feet can be used as grounding electrodes. The water pipe must be electrically continuous and must not have any insulated couplings or sections. A bonding jumper must be installed around any insulated couplings or sections. Thirdly, concrete encased electrodes. Concrete encased electrodes, also known as U for grounds, consist of at least 20 feet of bare copper conductor that is encased in concrete. The concrete must be in direct contact with the earth and must be at least 2 inches thick. The conductor must be at least 4 American wire gauge or AWG in size. Fourthly, ground rings. Ground rings consist of a bare copper conductor that is buried in the earth in a continuous loop. The ground ring must be at least 2 American wire gauge or AWG in size and must be buried at a depth of at least 2.5 feet. The ground ring must encircle the building or structure. Fifthly, plate electrodes. Plate electrodes consist of a metal plate that is buried in the earth. The plate must be made of iron or steel and must have a surface area of at least 2 square feet. The plate must be buried at a depth of at least 2.5 feet. The choice of grounding electrode depends on the soil conditions, the availability of water pipes, and the requirements of the local codes. It is important to select the appropriate grounding electrode and to install it correctly to ensure a safe and effective grounding system. Here are the steps for testing a grounding system after installation. Firstly, visual inspection. Visually inspect the grounding system to ensure that all connections are tight and secure and that all grounding conductors are properly sized and installed. Look for any signs of corrosion or damage to the grounding conductors or electrodes. Secondly, continuity test. Use a multimeter to test the continuity of the grounding system. Check the continuity between the grounding electrode and the ground bus in the main panel. Also, check the continuity between the ground bus in the main panel and the ground bus in any subholes. Thirdly, ground resistance test. Use a ground resistance meter to measure the resistance of the grounding system. The ground resistance should be as low as possible, ideally less than 25 ohms. If the ground resistance is too high, you may need to add additional grounding electrodes or improve the connections to the existing electrodes. Fourthly, voltage drop test. Use a voltmeter to measure the voltage drop across the grounding conductors under load. The voltage drop should be minimal, typically less than 3%. A high voltage drop indicates a poor connection or an undersized grounding conductor. Fifthly, touch potential test. Use a voltmeter to measure the voltage between the metal parts of equipment and the earth. The touch potential should be as low as possible, ideally less than 0.5 volts. A high touch potential indicates a fault in the grounding system. Regular testing of the grounding system is essential to ensure that it is functioning properly and that it is providing adequate protection against electric shock. It is recommended to test the grounding system at least once a year, or more often if there are any concerns about its performance. Understanding the color coding of grounding and bonding wires is crucial for safe electrical work. Firstly, green wire. Green wire is always used for the equipment grounding conductor. This wire connects the metal parts of equipment to the grounding system, providing a path for fault current to flow back to the source. Secondly, bare wire or bare wire, which is not covered with insulation, can also be used for the equipment grounding conductor. Bare wires are typically used in metal raceways or in direct burial applications. Thirdly, green with yellow stripe wire or green wire with a yellow stripe can also be used for the equipment grounding conductor. This color combination is commonly used in Europe and is becoming increasingly popular in North America. Fourthly, white or gray wire or white or gray wire is typically used for the neutral conductor. The neutral conductor carries the return current from the load back to the source. Fifthly, black, red, or blue wire. Black, red, or blue wires are typically used for the hot conductors. The hot conductors carry the current from the source to the load. It is important to note that the color coding of grounding and bonding wires can vary depending on the local codes. It is always best to consult the local codes before starting any electrical work. Never use a green wire or a bare wire for anything other than the equipment grounding conductor. Using the wrong color wire can create a safety hazard and can make it difficult to troubleshoot electrical problems. Here are some additional safety tips for working with electrical systems. Firstly, always de-energize the circuit before working on it. Turn off the breaker or remove the fuse that supplies power to the circuit. Use a voltage tester to verify that the circuit is de-energized. Secondly, wear appropriate personal protective equipment or PPE such as safety glasses, gloves, and insulated shoes. PPE can protect you from electric shock and other hazards. Thirdly, use insulated tools. Insulated tools can protect you from electric shock if you accidentally come into contact with a live wire. Fourthly, never work on electrical systems in wet or damp conditions. Water is a good conductor of electricity and can increase the risk of electric shock. Fifthly, if you are not comfortable working on electrical systems, hire a qualified electrician. A qualified electrician has the knowledge and experience to safely and effectively install and repair electrical systems. Remember, electricity can be dangerous. Always take precautions to protect yourself from electric shock.